Dozens of nations can stamp out an airframe, wire up avionics, and assemble a fighter jet. But look inside, and you'll find that almost all of them rely on imported power. Only about 5 countries on Earth actually possess the capability to build the advanced engines that make those jets fly. In 1986, India launched an initiative to join that highly restricted group. The goal was to build a homegrown powerhouse called the Cavari engine to propel their new Tahas light combat aircraft. Despite high-level funding and status as a national priority, the project slammed into a wall. The engine repeatedly hit its physical limits during testing, delaying the program for decades. The roadblock wasn't aerodynamics. The engineers knew how to design a shape that compressed air and generated thrust. The problem was that the physical materials they used simply could not survive the brutal environment inside the engine's core. Designing an engine on paper is relatively straightforward. Turning it into a working machine is a grueling war against the limits of material science and a severe test of a country's specialized industrial infrastructure. This animated diagram shows the inside of a jet engine, highlighting the hot section where fuel and compressed air ignite. Here, temperatures soar past 1,500 degrees Celsius, hotter than the melting point of the metals being used. At the exact same time, the turbine blades in this section are spinning at 15,000 rotations per minute. Under that intense combination of thermal and centrifugal force, standard polycrystalline metals experience a phenomenon called creep. The metal literally stretches and warps. As you can see at the microscopic level, the tiny boundary lines between the metal's individual grains become structural weak points, fracturing under the stress until the blade ultimately fails. Solving this required highly specialized metallurgical knowledge. But following India's 1998 nuclear tests at Pokran, sweeping technology sanctions were imposed. India's scientific community was isolated, blocked from purchasing the necessary materials or manufacturing expertise from abroad. They had to figure it out from scratch. The solution is the single crystal turbine blade. By growing a blade from one continuous metallic crystal inside a highly controlled vacuum furnace, engineers can eliminate those weak grain boundaries entirely, creating a structure that resists deformation under extreme heat and velocity. Mastering this highly guarded casting process is mandatory for modern aviation. Until India's defense program could produce these single crystal blades, the Cavari engine was stuck on the ground, proving material science dictates the limits of aviation. Even when scientists cast a structurally perfect blade, creating a working engine is only half the battle. A completed design means nothing until it proves it can survive real-world operations. This chart illustrates the massive scale of validation required for an aerospace-grade engine. A design must endure upwards of 10,000 hours of endurance testing. It gets subjected to high-cycle vibration fatigue, thermal shocks, and simulated bird strikes to verify that every component holds up over a full service life. This exposed another major bottleneck for India. They lacked the domestic high-altitude testing chambers needed to replicate the thin air and freezing temperatures of the upper atmosphere, while the engine was safely on the ground. Without those chambers, engineers faced a logistical nightmare. They had to ship the Cavari engine all the way to Russia, where it was strapped beneath the wing of an Illusian Il-76 flying testbed aircraft to gather actual high-altitude performance data. Relying on foreign testing facilities makes the process of designing, breaking, and iterating an engine almost impossibly slow. Building the multi-million-dollar infrastructure to test the engine is a requirement on par with designing it. After decades of intense trial and error, the persistence paid off. In 2021, India scientists achieved a historic breakthrough by successfully producing their own indigenous single-crystal turbine blades. While the Cavari won't power the Tejas fighter, the core technology isn't going to waste. A dry version of the engine is currently being adapted to propel India's Gatok autonomous stealth drone, and another variant is being tested as a marine gas turbine for naval vessels. To bridge the remaining gaps for their next generation of fighter jets, India is leveraging international partnerships. They are actively negotiating agreements with companies like the French aerospace giant Safran to co-develop future platforms. Building a jet engine requires a mature ecosystem. You need domestic precision manufacturing, a deep understanding of exotic metallurgy, and high-fidelity testing infrastructure, all maintained by thousands of highly specialized engineers and technicians. Designing and building a military jet engine entirely from scratch requires a country to master several distinct scientific disciplines simultaneously. There are absolutely no shortcuts in aerospace engineering, which is exactly why indigenous engine production remains the ultimate indicator of a nation's technological maturity and strategic sovereignty.